if x could equal a, that means that this would be a plus a, or 2a, or what? Now, that tells me that if I go all the way to the top of this and I replace a with 4, then this should make a graph and be continuous just like this is, but only now a equals 4. We don't have a question, so let's test it out and see. Now what we're saying is, so we can say therefore, g of x equals x squared minus 4 squared divided by x minus 4 for x not equaling 4. Second piece, it equals 8 when x equals 4. Let's see if it works. Take your inspires. Go home and pick up a new document. Some of you have been working on that for a while. I don't want you to be confused with other stuff you have, so let's go home and take up a new document, and let's do a graphs. Now, this is as much a review on how to put in a piecewise defined function into your Inspire as anything else. So if you don't know how to do that, pay close attention. We need a template for piecewise defined function. On the touch screen, the black ones, you've got the button right here. Okay? On the click pad, you have to do control multiplication. So on the click pad is control multiplication, and we have okay. Now, we've got the two pieces here. I'm trying to get this. This is not going to behave. Let's see if I can do it this way. There we go. Okay, that was set. So are you typing in? I'll get caught up with you. Got to put a fraction in there. Always go back to the original problem. Do not use anything but the original problem when you do work like this. And so I'm just going to then tab to get down to the other pieces. Now, how do I find that not equal to? If you're on the click pad, remember we got to less than or equal to with doing control less than and so forth. So on the click pad, you can do control equals, or if you do control on the catalog, you can also pick up the not equal to, there it is, right there in the middle. Okay, so you can do one of two things. If you're on the touch screen here, if you do control on the equal sign, you get another different kind of a little template, and either one of those you can then use as does not equal. So does not equal 4. I'm tabbing down. I've got 8, and we've got x equals 4. Okay, everyone have that in there, I assume. You can do that kind of typing once you know where the template is and tab key, and we get the nice little line here. Now, if I'm going to look at this, I'm going to change those dimensions a little bit. We could do a trace. We haven't done a trace on here yet, but if you do a trace, you go into menu and do a graph trace, and then a graph trace. And you can do that. I just will tell you that if you use the right, and then stop, the little icon keeps moving. Okay? So you might want to take note of that. The other thing to do would be to go in here and do points and lines and do a point on, which is what I'm going to do. And if I put a point there, remember how we need to verify whether or not this is true? I'll hover, open up, oops, a text box. If I change that and the point's not on there, but I can't see that it's not there, you know what's going to happen, don't you? Nice little message. Says you can't do it. Okay. So if you change that, do we get into a value? Is there a value there that we can have? Yeah. So the point does exist. Even though it does not exist on the first part of the function, it does exist on the second piece. And that second piece has plugged the hole that was left by the first piece. Okay. Now, one of the things that, again, to go back on this is we have to do that suppose. What if? And that's kind of the key to working this problem, not something that maybe you would have thought of on your own. So just be aware that you can do that, just like we do in the limit work. Okay, let's go on. Got more stuff to look at. Continuity of a composite function. It's a theorem. And we sometimes want to just kind of glide over these theorems, and we want them to go away, and we just want to work problems and not think about what it is, how we're doing them. We just want to follow the rules and plug numbers in and all that. But we can't do that. For full understanding, we have to understand every piece of this. So let's look at what we've got here. It says if G is continuous at C. First question I have for you. Is C an input value or an output value? Input or output? If we're going to be continuous, it means that the function is going to be able to be drawn, pencil definition, be able to draw from the left to the right without lifting the pencil at all. If I can draw from left to right, and I go through a point, and that point is at x, the input equal to c, then I know that it is continuous. So yeah, this is an input value here. So if the function is continuous at through that input value of c, and f is continuous at g of c, G is continuous at C, C is an input value, and F is continuous at G of C. Now, one of the rules of my class is that everyone has to have a chance to have some fun. And the fun is, of course, answering questions. Okay? So everyone has to have a chance to answer the question. So here we go. I want someone, I'm going to pick on this side of the room, someone over here. The function's continuous at G of C. Is G of C an input value or an output value with relationship to F? Someone over here. In function F, as it is defined here, is G of C an input value or an output value? And this is going to be where I get to test my knowledge here. Jordan, how do you know? Okay. It is an input value of function f. And if you look at the two statements, function g is continuous at an input value c, and f is continuous at. So in function f, this is an input value. Now, in function g, it's what? It's an output. In function f, though, by nature of the way this is written, it is an input. Then the composite function, f of g of x. Now, I had, on the quiz, not a lot of you, but I had a few people who looked at this notation and wrote it and worked it as if it were a multiplication problem. That is not multiplication between two functions. If it were multiplication between two functions, it would have to be this. Or sometimes some books and mathematicians will use this. This is not multiplication. This is our notation for a composite function. F of g of x. As it's written, what is g of x? What role does it play in this function? Yeah, again, it's an input. Okay? Again, it's an input. It's a composite function. Okay. Now let's see what this says. It is saying that if function g is continuous at c, Okay, so g of x is continuous at c, and f is continuous at the output of function g at c. Then the conclusion is the composite function is continuous at c. Well, let's look at our example down here. If we look at this example, I've got f of x is 1 divided by x minus 6, and g of x is x squared plus 5. H of x is f of g of x. Let's write that in another way. F of x equals f of... Now, some of you on the quiz missed this question, because I have here g of x, and I am, instead of writing g of x, I am writing something that is equivalent to g of x. When you see this symbol, we know it means equality. Equality of what, though? When it's used in this sense, what does it mean? It could be, we could use the result of that statement as for substitution. It means equal, but can you be a little more specific? What I'm looking for is this: the value of whatever's over here is the same as the value of what's over here. Isn't that what that equal sign means? The value of the expression here is the same as the value of the expression here. Equality is such a simple thing, but sometimes we don't realize what it really represents. So when I see g of x is equal to x squared plus 5, it means that the output value is equal to the output value. X squared plus 5 is another way of writing an output value. I am going to use the output of g of x. What's the output of g of x? X squared plus 5. Some of you missed that. Two ways of writing an output would be to use g of x, in this case, or x squared plus 5. Okay, since I have that, now that I have this information, this now becomes the input of function f, so I have 1 divided by. How do I use this input in function f? You see, this is the input value, and it says replace the input value with this input value. Why am I being so specific on this? Because we're going to mess this up royally in the next chapter if we don't understand it in this chapter. The output value of function g becomes the input value of function f, which becomes the input value or the replacement. Okay, so I end up with 1 divided by x squared minus 1. Okay. Now it says discuss the continuity of this composite function. According to our theorem, it says that function g is continuous at c. Now we got to talk about that value c. What value in our composite function are we going to have to be careful about? Or, we got two of them, right? 1 or negative 1. So we're going to have to be careful about x equaling 1 and x equaling negative 1, because that would make our composite function undefined. Well, let's see what happens. Is function g, so the first thing we're going to ask is g of x continuous at x equaling 1? Oh, thank you.